All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we have a beam here is supported by a pin and a roller. Let's find our support reactions. Anytime we're tackling support reactions, we know we're applying equilibrium equations. Anytime we use equilibrium equations, we gotta have a free body diagram that goes with it. For what it's worth, I've talked to professional engineers who, when they are hiring people, especially in entry level, they will, in technical interviews, say, here's a beam, draw me a free body diagram. And if people can't do it, they don't get hired. This becomes super important for us. Figure free body diagrams out. Figure out equilibrium. But let's go ahead and tackle this. So we know we're going to have to do a free body diagram. So we can model that as just a straight line in here. We'll just stick that directly below our given beam. I know at A, I have a pin. So I need to put in an AY. I'll assume it goes straight up. And AX. I'll assume it goes to the right. And those are just guesses. The math will let us know if we guess correct or not. 15 meters in. We'll say that's about right here. I have my roller. Roller should have one force perpendicular to whatever surface they're rolling on. Or that would be to the ground here. If the ground is horizontal, my force is vertical. So let's call that BY because it goes entirely in the Y direction. We know this first window here, this is 15 meters. And our second section is 5 meters. So we'll get both of those distances labeled. At the far right edge of this, there is a 75 kilonewton meter clockwise couple moment. 75 kilonewton meters. And in that 15 meter section, there's a distributed load in here. So I can replicate that. It's a rectangular one, so we'll just come in and draw a rectangle in here. Our number of arrows doesn't matter for us. Just make enough that it's obvious. I'm trying to show a distributed load. Kind of like this. And I can come in and say that is 10 kilonewtons per meter. 10 kilonewtons per meter. And that's it for us. From here, it's really just, can I apply equilibrium to find AX, AY, and BY? So start that out. We'll tackle, let's sum forces in the X first. It's by far our easiest one in here. Summing forces in the X direction. I'm going to get, I have AX, and that's it for us. There's no other X force in here. So I can just set that equal to 0. And my answer is just AX equals 0. As we move forward in our semester, hopefully your professor hits the point where they just say, just skip over this one. It's obvious on this that AX is 0. This is about the time distributed loads where I start telling my students that. If it's obvious AX is 0, just leave AX off and move on. But let's go ahead and find the rest of them. We can say, well, I have two unknowns in the Y direction, AY and BY. We can sum moments and figure one of those out. Summing forces in the Y direction isn't really a good approach for us because I'll have two unknowns in there. I still have to sum moments to find an answer. Let's find one equation, one unknown, if at all possible for us. So if I sum moments, I would do this at A. We don't have to. We could also do this at B, and we'd find AY out. There's multiple ways to solve these problems. Let's come down, and we're going to say with positive going counterclockwise, let's sum up our moments about point A. That's going to get me BY. BY is going to cause a counterclockwise rotation, so I'll put it in as positive. This is 15 BY. My couple moment is clockwise, so I'm going to subtract it off, 75. And I don't need to put a distance in here. It doesn't matter that it's 20 meters out here. We don't multiply moment by a distance. It's already a moment in here. Moment times distance, kilonewton meter squared, isn't something we use. I could have stuck that couple moment anywhere on here and it would have done the exact same thing. Don't multiply by distance on that. But then we'll go on and get our distributed load. So minus, I need force times distance on this. The force component of a distributed load is just what's the area of that distributed load. I have a rectangle, so the area is base times height. 15 times 10. Base is 15, height is 10. Let's even label that. This is for that distributed load, this is my force. And that force is just the area. That next piece in here, I need to get my distance for my distributed load. Distance is just going to be to the midpoint of a rectangle. Technically, it's to the centroid of whatever the shape is, but we're just going to use rectangles and triangles, or we can combine them and make a trapezoid. But for a centroid of a rectangle, it's the very middle of that. So what's the distance from A, where I'm taking moments about, to the very middle of my rectangle? Well, my entire base is 15. To get to the middle, I just divided by 2. 15 over 2 is my distance. That's my D term. Force times distance. And that's all that's going to cause moment. I can set that equal to 0. That will give me By is my only unknown in here. If I solve for By, I'm going to get that By is 80 kilonewtons. I get a positive number coming out for this, which means I guessed the correct direction here. It's going straight up. And that's going to be my first answer for everything. 80 kilonewtons going up, or that's technically my second answer. If I know By, though, I can sum forces in the y direction to finish my problem. Summing forces in the y direction. I have an unknown Ay going straight up. I have By going up plus 80. And I have my distributed load coming straight down. For a distributed load, again, we just want the area is the force. I'm summing forces. So I'll just say minus area. Base is 15. Height is 10. Equals 0. And again, that is my force equals the area. Force equals area for a distributed load. So that's where this is coming from. 15 times 10. Base times height, area of a rectangle. But I can solve for Ay from this one. I should get here that Ay works out to be 70 kilonewtons. And it's going upwards. I get a positive number out from this equation. I assume the correct direction matches my free body diagram. It's going up. That's my final answer for our problem. We can do distributed loads. We can get through these. We can do rigid body equilibrium. We've seen a bunch of videos to tackle that. But we got to be able to get these. Stick around if you're struggling with it. Watch more videos. We'll have more up for this. Hopefully this was useful for you. If it was, hit those like and subscribe buttons. Stick around. Let's get you in A with JJ.